Alvioli, talking about Nucleon configurations for heavy ion initial state and applications. So take it away.
Okay, thank you very much. Okay, my name is Alvioli. I am from the Italian National Research Council. I'm very sorry I cannot be there in person today, but I thank you very much. I thank you all for having me today. So what I'm going to be talk about for the next few minutes is work I've done with Mark Strickman, of course, from Pennsylvania State University over the last few years, and a few topics with Alba Soto, Jan Amelman, Antonio Bozic, and Anna Elfner. This is my outline. So this presentation is split in 3 parts. So as I said, in the first and second part, I will basically summarize most of the work we've done in the last few years about fluctuations in Monte Carlo Glauber modeling for proton nucleus and nucleus collisions. And then in the second part, we talk about additional fluctuations called color fluctuations, which we implement in Monte Carlo Glauber. And the last part is some work we recently developed, some application of all the machinery in the first and second part. And we've been looking at evidence for EMC effects for anti-quarks. So first part, nucleon correlations in Monte Carlo Glauber models. So briefly, Glauber approach. This is the quantum mechanical approach for high energy many-body scattering. Basic assumptions of Glauber approach is frozen approximation for the projectile traveling to straight lines trajectories. Inputs of the models are charge densities of nuclei and energy dependent nucleon cross sections. This is valid for PA and it's valid for AA, and one can describe interacting matter, spectators, and elastic scattering, and so on. As we all know, development of implementation of Glauber description with fluctuations is a Monte Carlo Glauber, which is an event-by-event simulation. In this case, the details of the density distributions of the participating nuclei are nucleon configurations. Nucleon positions in each configuration is generated at random, and in average, the collection of these nucleus configurations give the desired nuclear density. In Monte Carlo Glauber, of course, we talk about the number of participants in each event and the number of collisions, which are not measurable directly, but they give us a lot of information about the fluctuation, event-by-event fluctuations of collision geometry, and allows an increased precision in preparing initial states of colliding nuclei. Of course, multiplicity depends on participant and number of participants and number of collisions, and these quantities are directly related to centrality. Monte Carlo Glauber is a starting point for many models that require production points for individual subnucleon processes. And for example, Hygiene, Smash, Glissando, and so on, many models use this Monte Carlo Glauber description. So I've been working for a long time already on nucleon correlations in nuclei, and we implemented this higher order detail in nuclear configurations. What we do is to use a square of the wave function as a probability density to generate nuclear configurations, including correlations. Degrees of freedom of the wave function are nucleons themselves, and the wave function contains correlation functions. These are isospin dependent, and they are obtained from variational calculations, from nuclear structure calculations. And we, as you, of course, with the configurations, including nucleon correlations, we reproduce nuclear profiles, but we also ask to reproduce two-body densities. This is, sorry?
Patrick, can you go to that formula? So I just go back to that.
Sure.
Can you explain what the first formula? So you have a phi or a psi.
Psi, yeah, psi is a nuclear wave function. As I said, nuclear wave function is as nucleon positions, spins, and isospin as degrees of freedom. Usually, I mean, the zero approximation for a nuclear wave function is this phi in the right hand side, and that's a main field wave function. The F, R, I, J are called correlation functions, and these implement correlations which are neglected in mean field approximation. So we have the product of these functions F, which are function of the distances between pair of nucleons for every pair of nucleons in the nucleus.
But so the product is a bunch of two particle or two-point correlation.
Exactly. Yes.
They multiply on the near field solution, right?
Exactly. Yes, and these functions depend, as you see from the second formula, they depend on the distance between each pair of nucleons and their spin and their isospin, and also there's a tensor, so-called tensor operator, in this set of correlation functions.
And these are functions or operators?
They have a spatial dependence and they have an operator dependence. Okay.
Okay.
So very good. So we generate configurations which agree with the square of the wave functions assumed as a probability function, and in addition to reproducing the one body density of nuclei, they also reproduce a main feature of two body densities. What we mean, if we plot the probability of two nucleons as a function of the radial distance, as in the formula up here, what we get from mostly every many body approach, from small to intermediate to large nuclei, is of course you have a probability of two nucleons coming together at zero distance going to zero, and you have a maximum from this probability around 1 Fermi separation. And this is reproduced from by the configurations we produce in our Monte Carlo algorithm. As you see in the bottom, the figures in the bottom are obtained from these configurations, and you can clearly see difference of the radial two-body density for correlations, including correlations, the red curves, and the mean field configurations, the black curves. We can do this for a whole range of nuclei, and I will show a few applications of these configurations in the following. So, of course, within Monte Carlo Glauber, we can describe spectator nucleons, and most importantly, we describe participant matter distributions, which is relevant for hydrodynamic evolution. So we calculate moments, and we calculate the dispersion of the moments, and inclusion of correlations into the nuclear configurations mostly have an effect on the dispersion of the moments of eccentricity in particular, and we saw this in this publication. What we can do within the same Monte Carlo algorithm is to implement neutron skin in in the configurations. So this, of course, can be done easily by differentiating the proton and neutron profiles. For example, one application of these we did a few years ago was to calculate configurations with neutron skin for lead. And we, as an application, we checked some suggestion in the literature to use the existence of neutron skin as an additional tool for determination of centrality in the two figures in the left. And we found that the use of correlated configurations, in addition to something which I'm going to talk in a few minutes, which I described in a few minutes, called color fluctuations. We have a smearing of impact parameter, and we actually have an increase of the PN effective ratio, as in the right figure. As you see, the yellow bins are higher than predicted with the simple Glauber. Again, within the same machinery, we can, within the same Monte Carlo algorithm, we can implement nuclear deformations and any kind of deformations. Of course, in this case, we show figures about uranium, which I'm showing figures for delta epsilon 1, delta epsilon 2, and delta epsilon 3, where I distinguished both configurations. I mean, results obtained from configurations including nucleon correlations, and including or not including deformations. Of course, deformations give a larger effect for all the quantities, but also they and then correlations provides different results as a function of the number of participants. Another application of our configurations, our machinery to produce configurations, was to include both deformation and neutron skin, using this formula for the Woods-Jackson profiles for these for a number of nuclei, most notably for ruthenium and zirconium, which was discussed already, because it was the object of our study for the isobar run at RIC, and we considered this set of parameters for the Woods-Jackson profiles. For ruthenium, we implemented either deformation only. For zirconium, we implemented neutron skin only, or none of the above. And so we get results for the left figure show the difference with and without neutron skin as the ratio of the profile, proton to neutron profile, with and without inclusion of neutron skin. And we saw that the participant eccentricity in nucleus collision has a difference due to deformations at small impact parameters, and of course, as shown in the right figure. And also, neutron skin reduces the difference for magnetic fields, which was relevant for star collaboration. I'm not showing this here anyway, because I would like to move to part 2 of this presentation.
Can I ask a question before
of
you
course.
do that?
Yes, sure.
As you know, most people now who use Monte Carlo Glauber use a shortcut for the correlations, which is a hardcore separation that's minimum distance between the nucleons. And going back to some work that you did with collaborators, that was a good mock-up for spherical nuclei. Has that been retested for deformed nuclei, or can you say anything about that?
I would say we did not. I mean, I did comparisons many years ago with the excluded volume method, and I did not We did not repeat this recently. What I can say is now people, in my understanding, are looking for very high precision measurements and very high precision calculations. So the distinctive features of configurations generated with R Monte Carlo and including NN correlations, let me say the right way, would produce a totally different two-body density, as I tried to explain. So I would say if one looks for precision descriptions, and it is actually possible to use more accurate descriptions of the initial states of the initial configurations, I would say there's no need to use approximations, let's say, because it's really easy. One produces these configurations for the nuclei they like once and forever, and then they, in your application, you can read them from disk very easy, and it's as fast as using any other approximation. So I don't know if I answer your question, but that's what
It's fine. So
okay.
I have a comment here. For the zirconium 96, when you introduce neutron skin, what you introduce is by actually narrowing the proton distribution, right? I mean, so I think that since the charge radius is being measured, and what actually, if you look at the DFT calculation, what will happen is that what you should do is increase the AN, the neutron.
Okay.
I mean, so you will get a very different answer, because the way you are doing is narrow the proton surface. That means that the total nucleon surface becomes sharper. So your V2 actually in zirconium will be bigger because the overall nuclear surface actually effectively sharper. But the way I would say is in the introduce neutron skins to increase the neutron surface, then overall the matter surface actually become more smeared. So this actually totally make the ratio of the epsilon to goes the other way. Okay. So for your understanding of the CME, because I had the discussion with with the authors, and I convey this opinion. So I think they agree. So
okay. I think these are two distinct matters, right? Because in fact, I think there's a whole discussion about how to implement neutron skin, right? And you can play with these parameters in very different ways. But that's one point, and the inclusion of correlations in the configurations is a different point. I mean, they do not come together in a simple way.
I'm just only commenting for the mean field part.
Okay, very good. Very good. Okay, thank you. Okay, so let me move to part 2. And this part I will describe effects of color fluctuations and how we modeled hard triggers in Monte Carlo Glauber. What we mean by color fluctuations is in Glauber model, what happens is that the proton is described as a fixed entity. There's no different behavior it can achieve during the collision. Beyond Glauber approach, in the so-called Gribov-Glauber model, the proton in intermediate states can access a set of different states as in p-n diffraction, and this is very relevant at high energy. Because these different states at high energy effectively stay frozen during the interaction, during the time that the proton crosses the target nucleus. And so what happens is it may have different interaction strength as a function of these different state. It can fluctuate too. So this figure is tries to describe what happens in in Glauber approximation. So for each configurations, for each event, the intermediate states of the proton in PA stay frozen, and there's a number of interaction. It can an average number of interaction is it can suffer during the interaction. In the color fluctuation picture of this of the process, each different event can contribute in a different way, because the proton, it can access a different state, can have a different interaction strength, and on average you have a whole range of different interaction strength for each event, and you average over these different interaction strengths. So there's of course a relation of this phenomenon with color transparency and color opacity phenomena. The way we implement this machinery in of color fluctuations in Monte Carlo Glauber is rather simple. Instead of a fixed cross section, we use a fixed proton nucleon cross section. We use a distribution P of sigma, which has this shape, and the parameters entering this distribution P of sigma are fixed with these integral relations, when they are fixed with by observations. This was proposed a few years ago by Guzey and Strickman in this paper, and we used this color fluctuations description in Monte Carlo Glauber in a number of papers, trying to describe different phenomena and obtaining different results. One straightforward implication of fluctuations of the interaction strength of the projectile proton is a fluctuation of the number of wounded nucleons, the number of collisions for a given impact parameters. So this has an effect on centrality. There's a smearing of centrality, which I was referring to a few slides ago. And what happens is that probability of events with a large number of collisions is enhanced with respect to the usual Glauber approximation with a fixed total cross section. And also this has an implication on how centrality can be determined from different centrality classes can be determined as a function of the number of collisions, the distribution of the number of collisions. So instead of having fixed intervals of the number of, for each centrality class, fixed intervals for the number of collisions, we have distributions which overlap each other for each centrality class, as I'm showing in the right figure here. And this has implications for a number of observations. One other thing we implemented in a few papers was a mechanism to describe hard scattering in PA process. We developed a model to characterize the probability of events with a single hard scattering and n called -1 soft scatterings as a function of the number of collisions. This hard event in our description is triggered in a probabilistic way, using as a probability the product of the overall gluon distributions in the target, which is described by this f of rho exponential function for each nucleon. And these can be coupled in can be implemented in a Monte Carlo Glauber description using a random position for hard scattering point as depicted in this figure. We have tested these a couple application of color fluctuations and this geometry, this particular geometry for the determination of a hard scattering point against Atlas data a few years ago. And we got this nice agreement here with the conclusion that in this type of data, the proton has a smaller than average cross section, confirming that the color fluctuation description is a reasonable description. This machinery can be extended to a number of different arrangements. For example, if one wants to look at DA data, in which you have one has an incoming neutron instead of a proton, and still one has one hard scattering with one of the two nucleons in the deuteron, for example, the proton in red here, then one can still use this description for the geometry, for the hard scattering coupled with color fluctuations. And again, we tested the conclusions of this machinery against Phoenix data from the Phoenix collaboration, and with the similar conclusion in DA as in PA, that the proton suffering hard scattering has a smaller than average cross section, as shown here. Yeah, sure.
5 minutes plus questions.
Okay, 5 more minutes. Okay, I can do this. So very quickly, one additional application of the our model for the geometry of hard triggers can be extended to models of double partonic interactions, and we this figure here we have this kind of descriptions with two hard interaction points, and we implemented these to have a complete impact parameter dependence of double partonic interaction, and we can distinguish with these machinery events in which two digits are arising from this collision between one pair of nucleons or two pairs of nucleons. Okay, now I want to quickly move to part 3. In which we used some of these concepts I described to investigate energy loss effects and evidence for an EMC effect for anti-quarks. We considered preliminary data from Sequest experiment at Fermilab, which studied anti-quark distributions of nucleons and nuclei using Drell-Yan processes, and they probe distributions of anti-quarks for X between 0.1 and 0.45. And by studying the ratio of cross sections between one gets this RPA. These are the plots are the preliminary data, mostly from a PhD thesis by Arun Tadepalli. And what we did is first we checked what a Fermi motion approximation would suggest for this kind of processes, and our conclusions was that the optimal range to study this to search for an EMC-like effect for anti-quarks would be for X between 0.2 and 0.3, because it's around the crossover where the Fermi motion would be negligible for an EMC-like effect. But this is how this compares with actual data for carbon and iron, and conclusion here is that data is not compatible with prediction from Fermi motion. So this would go into the direction of an existence of EMC effect. Mostly, I would like to show these last 2-3 slides about how we estimated an energy loss effect for the quark traveling through the nuclear medium, because this is a competing effect for the search of an EMC-like effect for anti-quarks. So we studied this with the Monte Carlo code, with nuclear configurations we described, and with the mechanism I described for a hard trigger. So what we do is we simulate a hard interaction point at different longitudinal directions along the path of the projectile. And we know that the energy loss effect is proportional to the average gluon density traveled by the quark experiencing the hard interaction. So we estimated the strength of this energy loss effect using this formulation as a function of the position of Z hard, which is the hard interaction point. And we estimated an A dependence of this kind of energy loss effect. What we got is in the left figure here, where we consider the range of nuclei going from carbon to gold. And we also consider deuteron as a target, because actual data were shown as a function of cross-section of A over D over deuteron. So once again, in this case, also the behavior we would expect, I mean, the A dependence we would expect by this kind of effect is very different from what we can extract from the preliminary data. So we concluded that there might be a first evidence of an EMC effect for anti-quarks from this data. And okay. So I believe I just have time for this short summary. So what I told you is we generate nuclear configurations, including spin and isospin dependent nucleon-nucleon correlations. This was used, the configurations produced this way were already used by many others and for different purposes, including the ones I've shown in this presentation. We can produce with our Monte Carlo configurations for any nucleus with any number of protons and neutrons. We can implement the formation of nuclei. We can implement neutron skin as long as we have accurate parameterization of the proton and neutron single nucleon profiles. Then we implemented color fluctuations in Monte Carlo Glauber, which means we have an event by event fluctuating sigma and n cross section, and this is done by means of a probability distribution, a probability of having different values for the sigma and n. And this gives an important effect of the number of collision and in its relationship with impact parameter in each event. We developed a mechanism to model a hard trigger in high energy collisions, and eventually we used this machinery to estimate an energy loss effect and try and look in the sequenced Drellian data to look for a possible EMC-like effect for anti-quarks. And this is about all I wanted to say.
Good. I wanted to ask about your implementation of neutron skin. You said you did that in a halo-like model where you changed the radius. What was the reason for that? Because I'm asking because last week we had a discussion where several nuclear theorists argued rather vociferously against that. They said that if you come from nuclear structure, there are good arguments to implement it by a change in R rather than a change in A. Why did you choose the path that you chose?
I think we didn't have strong arguments about this point. We also had this discussion when we started looking at this thing, and the majority of us proposed to use this halo-like description, and that's what we did.
You could do it either way.
We can easily check the difference with different parameterizations, of course.
So I had a very related comment, first of all, on the functional form that you're using, and you're only treating A as the parameter to vary to describe your skin. But I think in general, one has to allow both R and A for the neutron to be different from that of the proton, and eventually the data should guide what is true. But my question really is that why are you adopting this parametric form when I think at the beginning of your talk, you mentioned about this probability density with the A body. So why don't you get density from that wave function that you are generating?
I believe this is an unsolved questions, even for nuclear structure experts. I mean, generating an exact wave function for like zirconium-96 or ruthenium-96 is an unsolved problem. And so this is actually an approximation, and I would say this is the best approximation we can afford to have for this large nucleus. I believe that high precision nuclear structure calculations, I mean high precision wave functions for nuclei have been established for, I don't know, like A equal I don't know, 16.
Yeah, I mean,
at this level of precision, of course, including nucleon correlations.
I do understand a model always has uncertainty. It's a model. But my point is that then are you using this A body wave function to describe the interaction? And if so, I find that this is a little bit inconsistent because you're using some wave function to describe the interaction, and then you're taking the density as something else.
I wouldn't. It's inconsistency. Is probably there to a certain degree. What we actually do is to extract correlation functions from the best the best we can do, for example, for smaller nuclei, because based on the assumption that nucleon-nucleon correlations are kind of universal, so they wouldn't change very much, or they wouldn't change at all across the periodic table. So we use the correlation function obtained from variational calculations for smaller nuclei and apply them as in the product you've seen to a mean field wave function for a larger nucleus. This is the best approximation I can give you of what we actually do. So yes, there's a bit of inconsistency, but yes, also the result you get for the radial dependence of the two-body density from these kind of correlated configurations is way different from what you would have from any other approach to prevent two nucleons to come from coming together at any time in your configurations. So I believe at this level, this is, as far as I know, I mean, this is the best one can do at this point to do something like this, to include the nuclear structure in these configurations.
Dean? Yeah, I just wanted to make a comment that the progress of nuclear structure ab initio has gone much further than what you said. You should take
probably,
a look at,
yeah. Not to ruthenium or zirconium, I guess.
No, there have been calculations of ruthenium zirconium that you can look at that are better than what you. But my actual question was about the these Jasper factors, these FRIJ to incorporate the two-body density that you bring in. When you do that, you actually change the one-body density, the rho of R as well. So do you adjust that?
No, we don't do that. We use a Monte Carlo. Let me tell you how we do that. We generate a huge number of nucleons in a large box, and then we select the right number of protons and neutrons at random, and we only keep those configurations where the one body density is okay and the two body density is also okay.
Yeah, but that reweights the one body density. So
no, it doesn't.
But
it does not. I can send you a sample set of configurations. You can check the one body density is what you put in there in the Wood-Saxon.
Yeah, I'm actually very interested in that, because if you can do that, we can use that for our calculations, which don't have the short range repulsion. So if you could, I'm Dean Lee, by the way. If you could send that to me, I would be very, very interested in that.
Yeah, if you send me an email, we can discuss further, of course.
Okay.
Sure. Thank you very much.
So I have a question about this global ripple picture. I mean, if you can show your slide 16, just a little bit some conceptual question.
Let me go back to that, and let me share my screen again.
So the proton size in this picture, so you first pick a small proton or big proton, then that proton will maintain the size and then close through the nucleus.
Yes.
I mean, okay, but if I take a proton as a collection of protons, so you mean all those protons in one configuration, they all like much more concentrated than the other? Is this like have a real support? I know you have diffractive measurements showing the cross-section changes, but we are talking about inelastic collision. Would this still apply to this picture?
I don't think so. I would say this. Okay, now first of all, what I'm describing here in this figure is the cross section is changing, means that each collision between the proton and one of the target of one of the nucleons in the target, that's the cross section that is changing. This is clear, of course, but I want to stress again. So, and this depiction here would say that the cross section is actually you can see it as how big is the area, this tube which goes through the nucleus, and how many inelastic interactions it goes through. So I wouldn't say, I would say no, the elastic collisions are not considered here.
Yeah, I understand, but just conceptually, you can really think the proton itself have a different size, that size is fixed.
Yeah.
I mean, okay.
No, it's not. It's not fixed. For given collision, it's fixed.
Yeah.
Yes, of course, for each event.
But are there actual support for this from the real inelastic experiment?
Okay, Mark can answer at this point.
Wow.
Now that you got into the conversation.
Well, you could calculate the fraction on nuclei. In some cases, the inelastic diffraction, and you reproduce it using the same P of sigma, and then that's probably, and when people of Atlas studied multiplicity distribution, P proton, what was lead collisions, they found that if they introduce, it gives them a better it gives them a better description of multiplicity distribution. They tried the shape is without, their statement was that without fluctuations in number of collisions, dispersion of multiplicity production is, they could not reproduce. With it, they got it pretty easily. but data indeed are so far limited, and hopefully people would get more from PA collisions in the next runs.
Thank you, Mark, and Sciliano. Thanks again.
Thank you very much.